This is ICS Fluid Flow Lecture number 3, Viscosity and Reynolds number, page 106. So we all recognize viscosity as a thickness of a liquid when we tend to pour it, like oils pour slowly and water pours quickly. Viscosity is defined as the measure of internal friction or internal resistance to flow. Now, when a fluid is moving at moderate to slow speeds, it moves in a laminar fashion. Laminar means layers. And the layer that's closest to the wall is essentially stationary, whereas each subsequent layer moving toward the center of the pipe moves faster. Now, Isaac Newton derived Newton's law for viscosity as follows. Consider a layer of fluid, this lower rectangle, moving at V1 in this direction. A layer which is farther from the wall would be moving more quickly, and this will be the second layer moving at V2. The distance between layers is dx, and the difference in velocity is dv. Take a look at this graph. It shows that as the shear stress, or force per unit area, increases on the fluid, units would be pressure, pascals, the shear rate increases. Increasing pressure causes increasing shear rate, or shear being tearing of the fluid's layers, and this relationship is in fact linear and proportional. The slope of this line is defined as absolute viscosity, and this relationship is true for what are called Newtonian fluids, fluids that behave in this fashion. The symbol we commonly use is the letter eta. Sometimes you'll see the symbol mu for absolute viscosity. So the slope of the line was the pressure, or shear stress, divided by the shear rate, which is velocity gradient. Pressure we know is force per unit area. The velocity gradient is the difference in velocity per unit distance between layers. Rearranging this equation, we have force per unit area, dx dv, and if we put units into this, in the SI unit, we cancel and wind up with kilograms per meter second. Pascal second is a unit of absolute viscosity in the SI units. In the CGS units, we'd have units of grams per centimeter second, which is called a poise. If we were going to use the British system, we'd have slugs per foot second. Take a look on page 108. Rheology is the study of flow, and it's bigger than viscosity. Viscosity is one aspect of rheology. It applies to many types of fluids, including muds and sludges and suspensions and polymers, etc. Take a look at the graph on the right. Here we have a Newtonian fluid whose strain rate, or shear rate, increases proportional to stress. Take a look at the blue line just above it, called pseudoplastic. A pseudoplastic fluid. What's going on here? As the stress is low, notice that the strain rate is very low. It's not moving very much. It's resisting strain or tearing or shearing. But as the stress increases, then the fluid shears to a greater extent. That is, it is undergoing shear thinning. So under higher pressure, the fluid thins out. What kind of fluids behave like that? Well, ketchup is an example. When you squeeze the bottle slightly, you get a little bit of ketchup, and when you squeeze the bottle a little more, suddenly you get a lot of ketchup. So the fluid undergoes shear thinning, or thins out. Now, quicksand is said to behave that way as well. The harder and faster you resist, the thinner the liquid gets, and one sinks faster, presumably. There was another term shown there, and it was called pseudoplastic. Now, the word pseudo means like, so this is a fluid that behaves like a plastic. Well, then in what sense is that true? If you take a film of plastic and stretch it between your fingers, you'll find that initially it doesn't stretch very much, but when you exceed a certain amount of pressure, it suddenly pulls apart rather easily. What's actually happening is the polymer chains are unraveling. And so in that sense, if a fluid behaves like a plastic, it is pseudoplastic. It's undergoing shear thinning. Take a look at the red curved line below the Newtonian fluid. What's happening here? Well, under low stress, this fluid shears quite easily. Its strain is large, but as the stress increases, it starts to thicken up or resist shearing. And the term for that is shear thickening. Shear thickening. Such fluids are called dilatants. Dilatorius in Latin means delaying, and in English we have words like dilly-dallying, or causing delay. So it's almost as if there's a delayed resistance. An example of shear thickening can be seen on sand at the water's edge. If we are standing in the sand, we're applying relatively low pressure and tend to sink. That is, the sand is more mobile, has low viscosity. However, when we run across the surface and impact the sand with higher pressure, the sand is hardened. That is, it becomes shear thickened. There's one final type of fluid to discuss, and that's called a Bingham Plastic. Notice that there's no shear whatsoever until a threshold limiting pressure is applied, and at that point then the fluid shears more or less proportional, like a Newtonian fluid. What kind of fluid behaves like a Bingham Plastic? A common example would be toothpaste. You squeeze the tube lightly and simply nothing comes out, but if you reach that threshold pressure, then it comes out proportional to the pressure applied. I want to briefly mention the difference in viscosity of gases compared to liquids as a function of temperature. If you look at the graph here on the right, the lines that are decreasing as temperature increases are water and mercury and oils. These are all liquids. And that's a familiar concept. As liquids become warmer, the viscosity decreases. However, the lines that are increasing are gases: hydrogen and helium and air. For gases, their viscosity actually increases with temperature. What is going on? Molecules in the liquid state experience relatively strong intermolecular forces because they're close together. These intermolecular forces are responsible for a liquid's viscosity. If you increase the temperature of a liquid, it causes the kinetic energy to increase, and the molecules become more mobile, and that reduces their intermolecular attraction. It reduces their viscosity. In fact, if you continue to heat the liquid, the kinetic energy will exceed the attractive force or binding energy, and the liquid will ultimately boil. Those are liquids. What about gases? Remember that in gases, the molecules are very far apart and they experience little to no intermolecular attraction. And so heating a gas increases the kinetic energy of the gas molecules, resulting in greater rate of collisions. And this in effect slows down the translational or directional motion of a gas, hence increasing its viscosity. Think of trying to run to a bus on a street where there are very few people in your way, and you can have a direct path. On the other hand, if you're trying to run to catch your bus and there are literally hundreds of people crowding in front of you, your path would be a zigzag pattern and your effective translational velocity would be decreased. The importance of this difference will be apparent in analytical courses using gas chromatography later on. On page 108, we have a few interesting applications of viscosity. Let's talk about motor oils first. So when an engine is in operation, the piston is rising and falling within the cylinder block during the compression stroke and then being pushed back during the power stroke. And during these cycles, we need a tight seal between the piston rings and the cylinder head. And metal against metal is not effective. There'd be a tremendous engine wear, causing loss of power by escaping gases as well as pollution. So it's oil that provides the seal between the two metal surfaces. Now it's said that about 70% of the engine wear of a car occurs within the first 30 seconds after startup, and that's because the pistons are dry, the rings are dry, and oil needs to be sprayed up to coat the surfaces. So we need an oil that at low temperatures, here's our temperature, at low temperatures we want an oil that's relatively thin, that'll quickly coat the cylinders and protect. This is especially true in cold weather where the oil would thicken otherwise, so we need a thin oil that'll spray up quickly. However, at high temperatures, the problem is the oil thins out quite a bit, and it doesn't provide enough insulation or protection between metal surfaces. So at higher temperatures, we need an oil that is, in fact, thicker. So the SAE number is an indication of thickness. A 10 oil is thin and a 30 weight is thicker. Engineers have come up with what are called multigrade oils, such as 10W30. This is an oil that is thin at low temperatures, and although it does thin out a bit, it's not as thin as it otherwise would be at higher temperatures and gives better protection. So it's called 10W30. At cold temperatures, it performs as a 10 weight oil. At high temperatures, it performs as a 30 weight oil. How do they do this? Well, they add polymer additives to change the viscosity of the oil. So polymers are long chains of molecules, and they're typically very coiled up at low temperature. And as the fluid moves, these coils of polymers just slide past each other. They feel relatively little attraction. But at high temperatures, these chains unfold. And as they're unfolded, there's more surface area, more intermolecular attraction, and they tend to increase the viscosity, helping to offset the natural decrease in viscosity that would otherwise occur during heating. A multigrade oil. There's a couple other applications mentioned here related to fighting fires, reducing viscosity of water by firefighters using certain additives, and also dolphins attain high speeds by secreting slime that reduces the viscosity at their skin level. I'll let you read about that. On page 110, let's look at types of fluid flow, specifically laminar flow versus turbulent flow. So laminar flow is, as the name implies, the fluid is flowing in layers. The fluid is also described as being viscous or streamlined, hence the pattern of flow. If velocity increases beyond a certain critical value, then eddy currents start to form. Here are some eddy currents which literally tear the liquid away from the surface of the pipe. And the laminar flow pattern is changed and the flow becomes turbulent. Now the critical value of velocity occurs when Reynolds number is equal to about 2000. In practice, it's found that if the Reynolds number is less than 2000, the flow is laminar, also called viscous or streamlined. If the Reynolds number is greater than 4000, then the flow is turbulent. And if the Reynolds number lies between 2000 and 4000, the flow is critical. It's in a transition state, changing between turbulent and laminar, and vice versa. This diagram shows a cross-sectional velocity of a fluid relative to distance from the center of the pipe. So at the walls, the velocity is essentially zero, and as we move toward the center of the pipe, the velocity increases in a rather uniform fashion. That's the case of laminar flow. In turbulent flow, the pattern is less even, more erratic. A practical method of visually finding the point of transition is a setup as I show here. So here we have a pressure tap in a pipe, and a dye is being extruded into a flowing liquid. Now, provided that this pipe is made of glass or some transparent material, we'll be able to see a straight flow of the dye in the case of laminar flow. In turbulent flow, the dye would be quickly dispersed, and in transitional flow, it would be somewhere in between. On page 111, we are given the formula for Reynolds number. Reynolds number is calculated as the diameter, the cross-sectional diameter of the fluid, which would be the internal diameter of the pipe, the average velocity of the fluid, its mass density divided by its absolute viscosity. Let's calculate Reynolds number. So oil with a specific gravity of 0.765 and an absolute viscosity of 1.70 centipoise is pumped through a 4-inch Schedule 40 steel pipe at a flow rate of 150 imperial gallons per minute. Calculate the Reynolds number to 3 sig figs and state whether the flow is turbulent, laminar, or transitional. And there's the answer. So again, we're going to use the formula for Reynolds number. We'll need the internal diameter of the pipe times the velocity of the fluid times the mass density of the fluid divided by its absolute viscosity. We're given some of these. Here's the viscosity. We'll use a specific gravity to calculate the mass density. We're told that the pipe is a 4-inch Schedule 40 pipe. We'll get the diameter from that. And we'll have to use the flow rate to determine the velocity. Let's start with the diameter, and notice that a 4-inch Schedule 40 pipe is being used. Now a 4-inch Schedule 40 tells us the nominal size, not the exact size. We need the internal diameter. If you go to page 129, we'll show you how that's done. When you read the self-study unit on pipes, fittings, valves, and pumps, you'll be introduced to schedule numbers. Schedules refer to wall thicknesses. There are in fact 11 scheduled numbers ranging between 5 and 160. Schedule 40 is standard wall thickness. Schedule 80 is double wall thickness, as shown here for higher pressure applications. So referring to the table, we find the nominal size. We want 4-inch. We need then the second column, which is schedule number. In this table, Schedule 40. That gives us then the outside diameter in inches, 4.50 inches. And we want as well the wall thickness, which is given as 0.237. Using the outside diameter and thickness, we can calculate the inside diameter. Let's go back to page 111 to do that. So over here I have the calculation of the inside diameter. The inside diameter would be equal to the outside diameter minus 2 of these wall thicknesses. So here we have inside diameter is equal to the outside diameter minus 2 times the wall thickness, or 4.026 inches. So here I have Reynolds number equation. The diameter is 4.026 inches. Now I want to do this first in the SI system, so I need to convert this to meters. I'll multiply inches by 2.54 centimeters per inch, and then divide by 100 to convert centimeters to meters, and I have 0.1023 meters is the diameter. For the velocity, we're going to use the formula Q equals A times V, and rearranging gives V is Q over A. Now the area we'll get from pi d squared over 4. We just said that the diameter is 0.1023 meters. We'll square that times pi over 4 is 0.00821 square meters. That's our area. We need the flow rate, but we need it in cubic meters per second. So we're given 150 imperial gallons per minute. We'll divide by 60 to give us imperial gallons per second. And then I'm going to use the conversion. There's 4.546 liters per imperial gallon. That'll give me liters per second. And finally, we'll divide by 1,000 liters per cubic meter to give us a flow rate of 0.001137 cubic meters per second, divided by the cross-sectional area of 0.00821 square meters, gives us a velocity of 1.384 meters per second. So here's our velocity term. Now we need the mass density. That'll have units of kilograms per cubic meter, but we're given the specific gravity, which is 0.765. How do we convert that? Well, recall that the specific gravity is numerically the same as the mass density in the CGS system. So 0.765 specific gravity is the same as 0.765 grams per cubic centimeter. Then it's just a matter of converting grams per cubic centimeter to kilograms per cubic meter. So we'll divide by 1,000 to convert grams to kilograms, and we'll convert from per cubic centimeter to per cubic meter by multiplying by 10 to the 6th. Just follow the units, and it's 765 kilograms per cubic meter. Now, if you think about this, you probably at this point know that the mass density of water in the SI system is 1,000 kilograms per cubic meter. And if you think that 0.765 is just 76.5% of that value, that's 765 kilograms per cubic meter. There's our mass density. Finally, we need the absolute viscosity, and we'll need that in units of kilograms per meter second in the SI system. Now here we're given the absolute viscosity is 1.70 centipoise. I divide by 100 to make that 0.0170 poise. And a poise has units of grams per centimeter second. We need to convert that to kilograms per meter second, so simply convert grams to kilograms, dividing by 1,000, and convert from per centimeter to per meter, follow the units, multiply by 100, and that gives us 0.00170 kilograms per meter second. And here's that value. So if you combine all these together, you'll find the Reynolds number is 63,700. And the units cancel. What kind of flow is that? Well, clearly it's greater than 4,000, so that would be turbulent flow. This was done in the SI system. I'd like to do it with you also in the British system. Same again. So in the British system, we need units of, well, British units. So here we have the internal diameter is 4.026 inches, divided by 12 to convert to feet, 0.3355 feet. We'll need the velocity. We could just convert it from the metric units, but let's go back to the basics here. Again, V is Q over A. The area is pi d squared over 4. So it's pi over 4 times diameter squared, and that's 0.0883 square feet. I'm going to use the flow rate of 150 imperial gallons per minute. We want to convert that to cubic feet per second. So from minutes to seconds, divide by 60, And you have this conversion available to you in your test aids. 1 cubic foot is 6.23 imperial gallons. Again, just follow the units and cancel. This works out to be 0.4013 cubic feet per second, divided by 0.0883 square feet is 4.54 feet per second. And that's our velocity term here. We need the mass density, this time in terms of British units, slugs per cubic foot. Well, you may recall that the density of water in the CGS system was 1 gram per cubic centimeter, and that's equivalent to 1.9403 slugs per cubic feet, so you could simply use that conversion factor here to convert. The mass density is 0.765 grams per cubic centimeter times 1.9403 slugs per cubic foot per 1 gram per cubic centimeter, so we have 1.484 slugs per cubic foot here. And finally, we want the absolute viscosity in British units, which will be slugs per foot second. So to convert absolute viscosity, I'm going to go back to a conversion factor given on page 107. I've cut and pasted it here for us to look at. 1 centipoise is equal to 2.089 times 10 to the minus 5 slugs per foot second. Recall that we have 1.70 centipoise is simply a matter of using that conversion factor to convert to British units. And I have it right here. 1.70 centipoise times 2.089 times 10 to the minus 5 slugs per foot second per centipoise gives us 0.0000355 slugs per foot second for absolute viscosity. And working this out is 63,500, essentially the same number as we had previously, but this done in the British system. So there's the calculation of Reynolds number, and that's probably enough for this lesson.